This apple is at the center of the universe. There are roughly 100 million cells inside an apple, and 10 to the power of 25 individual atoms, each one stretching for no more than a nanometer across. The highest number of things that you could fit inside an apple would be roughly 10 to the power of 102, measured in the smallest possible cubic unit, a Planck volume. Looking upwards, you could fit roughly 100 apples inside the volume of the average person, and about 10 to the power of 25 inside the volume of the Earth. Roughly 10 to the power of 66 could fit inside the Milky Way, and around 10 to the power of 84 could fill the entire extent of the known cosmos. And so the apple and you sit at a nexus, a confluence of competing forces, interactions, and laws. A place where all the competing powers of the universe reach an uneasy truce. The apple is at the balance point of sizes in the universe. The apple, at about 10 centimeters across, is roughly 35 orders of magnitude larger than the Planck length, the smallest conceivable measure of distance, and it's about 27 orders of magnitude smaller than the observable horizon of the cosmos. And so, 62 orders of magnitude separate the smallest to the largest scales within the universe. A random number that describes the entire cosmos and all its components. At least, it may seem random at first. For halfway to the bottom, halfway to the top, the apple is at the center of the universe. And why it sits precisely at that balance point may explain why the cosmos exists at all. In 2013, NASA's K-10 rover, while being tested at Ames Research Center in California, was remotely controlled from a pretty extreme location. Space. Astronauts aboard the International Space Station guided its movements and science operations using a laptop interface and live data links. A remarkable feat, and one that opened up the possibility of humans being able to command robots on Mars and the Moon from orbit. Sometimes it's useful to be able to control your tech remotely, perhaps not in deep space, but certainly on the other side of the globe. And so if you're looking to remotely control your computer for personal or business reasons, AnyDesk can help. AnyDesk is a lightning-fast remote access tool that makes it feel as if you're sitting right in front of the remote machine. Indeed, here at History of the Universe, we find it great for video and audio editing whilst away from the main machine, and also very useful for transferring large files. AnyDesk's secure, direct file transfer bypasses the cloud entirely. This is ideal for us to move high-quality footage or even entire documentaries around between team members, and could have any number of uses for other businesses and projects. And AnyDesk is available across all major platforms, is backwards compatible with older operating systems, and has 99.98% uptime reliability, so you can depend on being able to use it when you need to. And what's more, personal use is totally free, with tailored plans for team and business environments. And so, head to anydesk.com to try this premium remote access tool, free of charge. As I began my university studies, I asked my venerable teacher for advice regarding the conditions and prospects of my chosen field of study. He described physics to me as a highly developed, nearly fully matured science, and that theoretical physics is noticeably approaching its completion to the same degree as geometry did centuries ago. So said Max Planck of his teacher Philipp von Jolly, under whom he studied in 1875. And 25 years later, Max Planck would, to the consternation of his former mentor, almost entirely revolutionize the supposedly fully matured science of physics. And he didn't even mean to. Planck had been hungry for a physics education, but he'd found his lectures to be stuffy and old-fashioned. Besides the remonstrations of von Jolly, he also considered his professors Hermann von Helmholtz disorganized and slow, and Gustav Kirchhoff dry and monotonous. So he largely taught himself, the perfect recipe for a revolutionary. At the close of the 18th century, Planck was attempting to mop up what von Jolly would have considered one of the final long-standing puzzles in physics, mathematically describing the spectrum of radiation emitted by hot, glowing things, like a metal poker taken out of a fire. Genius after genius had tried their luck to no avail, but the joke goes that there are two kinds of physicists, those who play by the rules and those who get physical constants named after them. And so Planck persisted, and after exhausting all other possibilities, he introduced what he called a mathematical trick. Instead of pouring out light in all possible quantities, Planck assumed that these hot objects could only emit discrete chunks, or quanta, of radiation. He then introduced a special number to describe the smallest possible chunk of light, a constant. And so the unstoppable fires of revolution were lit. By Planck's time, physicists had already grown accustomed to physical constants. Of course, there are artificial ones, created by scientists, standardized measurements of space, time and weight, like the ounce and the meter. But more importantly, and more fundamentally, there were some that seemed to pop out of theories of nature, like Newton's constant that described how strong gravity was, or the speed of light, values that seemed to have no explanation. They just were. But despite centuries of consideration, no constant had ever described something so tiny as that which Planck used to describe quanta of light. Indeed, the most precise measurements at the time were around 1/1000th of an inch, or a few microns. With this kind of equipment, scientists could study bacteria and the internal structures of cells. But Planck's constant went far, far beyond that. This number tells us where and when and how quantum effects become overwhelming, where the certainties of the world we know melt away into probabilities and uncertainties. At roughly equal to 6.626 times 10 to the power of minus 34 joule seconds, Planck was able to combine this constant with three other constants, the speed of light, Newton's gravitational constant, and Boltzmann's constant, to create a system of reference points for the quantum world. And these are the Planck units. A Planck time of around 10 to the power of minus 44 seconds, a Planck energy of around 10 to the power of 9 joules, and a Planck length of around 10 to the power of minus 35 meters. These units tell us that any object, system, event, or occurrence that approaches these limits will be affected by the world of the quantum. And as to what happens when systems reach the Planck limits, nobody knows. These seem to be the limits of the universe. Beyond these numbers, quantum chaos rules, and our mathematics does not allow us to go. However, we shouldn't worry too much, because we're unlikely to run up against these limits anytime soon. The world's most powerful particle accelerator is the Large Hadron Collider, with a peak design collision energy of 14 tera-electron volts, which is 14 times 10 to the power of 12 electron volts. If they collided a tennis ball with that energy, it would burn as bright as 100,000 Hiroshimas. And the most energetic particle we have ever detected anywhere was the so-called Oh My God particle, a cosmic ray with a whopping 3.2 times 10 to the power of 20 electron volts, over 40 million times more powerful than the particles in the LHC. The Planck energy is almost 40 million times again more energetic than that. In 2020, a team of German scientists shot X-rays into a hydrogen molecule. The X-ray photon bounced off one electron, sending it scattering away, then ricocheted off another, sending the second one free. The two electrons then interfered with each other. The scientists were able to measure the interference pattern and deduce exactly how long it took for the photon to bounce from one electron to the other. 247 zeptoseconds, the shortest duration of time ever measured. A zeptosecond is roughly a trillionth of a billionth of a second. The Planck time is another 23 orders of magnitude shorter than that. And finally, attempts to measure the size of the electron by trapping it in an electric chamber show that it must be no bigger than 10 to the power of minus 22 meters, the smallest measurement ever made. The Planck length is 1,000 billion times smaller than that. the world of the Planck scale is unknown to modern science, hidden from view with even our most advanced instruments. Although, thanks to quantum field theory, we do have some insights as to what might happen at those impossibly small scales. In 1941, Werner Heisenberg made a trip that would change his entire career. He visited his longtime friend and mentor, Niels Bohr, in Nazi-occupied Copenhagen. During a conversation, Heisenberg brought up nuclear weapons, although his intentions and motivations were unclear. Bohr understandably assumed that Heisenberg was trying to encourage him to join the Nazi atomic weapon effort, which horrified him. The two parted ways on uncertain terms, never to speak directly again. However, the details of the story remain uncertain. Heisenberg insisted that his goal was not recruitment and that Bohr misunderstood him, and indeed Heisenberg's work in general in World War II remains ambiguous to this day. We know that he worked for the Nazis in their attempts to develop a nuclear bomb, although he always maintained that he intentionally slowed down and delayed the Nazi bomb project. A suitably uncertain fate for the man who brought uncertainty into the quantum world. Decades earlier, at the height of the quantum revolution of the 1920s, Heisenberg had proposed something about the quantum world completely unlike anything experienced at macroscopic scales. His uncertainty principle stated that it was impossible to measure both the position and momentum of a particle to infinite precision. You measure both to some degree of uncertainty, but the only way to pinpoint one property exactly was to give up knowledge of the other. While Heisenberg imagined this roadblock in terms of light hitting matter, a high-precision beam would knock a particle away, while a lower-power beam would remain imprecise. Later work would reveal that it was a simple fact. This is just the way nature is, the same way that gravity exists and light moves at a constant speed. And the number that describes the seesaw relationship between the two properties, none other than Planck's constant, the ultimate arbiter of the quantum world. Heisenberg's uncertainty principle tells us that the quantum fields that soak space-time are never quite still. Even with no particles buzzing around, the fields have a fixed amount of unknown energy, a certain amount of ground state vibration that refuses to leave. And at the Planck scale, these vibrations cause space and time themselves to distort beyond all recognition. At macroscopic scales, well and safe above the Planck length, space-time is as smooth as a thin rubber sheet. There are divots and hills and valleys, and ripples too, but it's all unbroken. There are no jagged edges, no loops or twists or folds. But the uncertainty baked into the quantum fields causes energies to rise and fall, particles to appear and disappear, their existence allowed by uncertainty as long as they are brief enough not to be noticed. Because of that energized chaos, space-time itself bends and flexes in response. This is the quantum foam at the Planck scale, roughly 10 to the power of minus 35 meters, the fundamental substrate of reality at the smallest possible distances. A region where tiny twists and whirls of space-time compete for dominance before vanishing without a trace. Tiny wormholes connecting one pocket of space to another before blinking out of existence. We have no way of describing the nature of reality at these scales. Einstein's general theory of relativity demands that space-time must be smooth. Quantum field theory says that it is not. Indeed, the Planck scale is so small that many scientists doubt if physics, or even reality as we currently understand it, could ever make sense of it. And so, to try our best to unravel this, let's go to the cinema. Films are not really continuous. They're a series of individual pictures played back at a speed of 24 frames per second. Our perception blends the pictures together into a smooth, seamless whole, giving the illusion of fluid movement and continuity, when in reality, no such continuity exists. But if you could perceive the movie at a quantum rate, giving yourself enough time to observe each individual frame, the illusion would shatter, and you would see the succession of staccato images for what they really are. And so is time quantized? At the Planck scales, does our sense of continuous movement through time break down? What about space? We perceive motion to be fluid, not a series of staggered snapshots. But are our perceptions fooling us? We've been able to measure minute intervals of time displacement in space, but even with our most advanced instruments, we can't even come within a fraction of the Planck scales. So just what is going on down there? Do time and space even exist in any meaningful way? And if they don't, then how does the structure of the universe arise? The apple may give us a clue. The smallest known force interaction is the weak nuclear force, one of the 4 fundamental forces of nature. It has a range of only 10 to the power of -18 meters. So of course an apple existing at the Planck scale would be far smaller than this. It would feel the weak nuclear force, along with the strong nuclear force, the electromagnetic force, and gravity, all combined, and all strong. Indeed, only in the first few moments of the Big Bang, when the universe was but a second old, did the rest of macroscopic nature experience these kinds of unknown physics. And at Planck scales, physicists even believe that all the forces of nature meld into a single, unified whole. Although what properties that unified force takes, nobody has been able to discern. So what becomes of our apple? Unsurprisingly, nothing good. According to our best guesses, the apple collapses to form a singularity, a point of infinite density. Pretty final, or so it may seem. In the speculative theory of loop quantum gravity, space-time is discrete and quantized at the Planck scale. In this theory, there would be no such thing as singularities. In loop quantum gravity, there is the smallest possible size, a pixelation to space-time that prevents objects from getting any smaller than that. So maybe our apple would become stuck at the Planck scale, the smallest possible unit of measure in the universe, unable to compress further. There it would experience forces and energies unknown to modern science. It would have a direct view of the quantum foam that permeates the cosmos. Thankfully, however, both for the apple and our prospect of a nice mid-morning snack, our apple is much larger than the Planck scale. At 10 centimeters in diameter, over a trillion Planck lengths could fit side by side across the apple. Indeed, it's so large compared to the Planck scale that it might as well live in an entirely different universe. It is so far removed from the chaotic foam of quantum uncertainty that permeates space-time. But that is not quite the case, for there is a step between Planck and the apple. To build macroscopic objects, you need a bridge. To make an apple, you first need atoms. We must be clear that when it comes to atoms, language can be used only as in poetry. The experimenters carefully calibrated their laser. Their target? A single hydrogen atom in the center of the chamber, chilled to almost absolute zero. Their goal? To take its picture. First proposed in 1981 by Russian theorists, it would take until 2025 for someone to finally make it work. The idea was to hit the electrons and let them scatter away, then carefully measure their velocities in a way that experimenters could reconstruct their original positions. Repeated again and again, each experiment could build up, one shot at a time, a portrait of the atom. And what they saw was bizarre. A series of overlapping rings, clusters, and gaps. What they were mapping was not the electrons themselves, but the waves of probability describing where the electrons might be. Each fire of the laser encountered the electron in one particular position. Then another found it on the other side of the atom, for example. Then again and again. Where the waves crested showed where the electron was found most often. The gaps, where it was never found. The atom itself is roughly 100,000 times larger than the electron, and roughly 10 to the power of 25 times larger than the Planck length. And so already, at even these subatomic scales, we are unfathomably far from the deepest structures in the universe. But why is the atom this big, and no bigger or smaller? Indeed, why are all the atoms of the same element identical throughout the cosmos? It's as if every skyscraper in a city was exactly the same, made of the same materials and roughly the same size. There must be something universal and fundamental about them. Of course, the image taken in 2025 of a real atom differs greatly from our popular conceptions of it. A central core surrounded by electrons circling in their orbits. The atomic symbol is everywhere. Indeed, it's become so commonplace that it even stands in as the generic symbol for all of science. It is inaccurate and outdated, but it did represent the first modern attempt to understand what an atom looked like. And the man who created that image and started our journey to a true understanding of why an atom is the size and the way it is, didn't get off to a particularly promising start himself. The young Niels Bohr, who someday would become Heisenberg's mentor and estranged friend, was not an apt pupil in the chemistry lab. He had a fondness for mixing together chemicals that shouldn't strictly be mixed, leading to explosion after explosion. Indeed, he was an expert at breaking glassware, and when students would hear a muffled boom coming from the lab down the hall, the saying was, "Oh, that's a Bohr." And so without a doubt, it was better for everyone that Bohr turned his attention to theoretical physics. At the beginning of the quantum revolution, Bohr had quickly become interested in atomic physics. He was especially drawn in two directions. One was the quantum ideas of Max Planck, that certain quantities in the universe could only act in discrete lumps. The other was the work of his mentor, Ernest Rutherford, who had discovered that whatever the atom was made of, it had a small, dense, positively charged core, a nucleus. Bohr wove these two strands together to paint a first portrait of the atom. At the center of Bohr's atom sits the nucleus, a tight, compact ball of positive electric charge, agreeing with Rutherford's experiments. But what about the electrons, the points of negative electric charge that exist around the nucleus? Other scientists thought that they might form a plum pudding, a thick soup spread out over space. Instead, Bohr replaced this with mostly nothing. Bohr conceived of the electrons as particles, with their relationship to the core governed by electrostatic attraction. Their negative charge pulled as close to the positive nucleus as possible. But this situation should lead to collapse, with each atom unable to hold itself together. So Bohr turned to the quantum world to solve this problem. Electrons could not get any closer to the nucleus because their orbits were quantized. Unlike planets around the Sun, which can have any orbit they please, the electrons had to choose from discrete, specific orbits. For a simple hydrogen atom with only a single proton in its nucleus, the nearest an electron can approach is called the Bohr radius, equal to roughly 10 to the power of 24 Planck lengths. Of course, that is far, far larger than the nucleus itself, which is typically no wider than a few femtometers, about 10 to the power of 20 Planck lengths. That makes even the smallest atoms over 99.99999999999% empty space, with their extent governed by the competing relationships of electrostatic repulsion and the quantization of angular momentum. And so, Bohr's model was a first step into a quantum view of the atom. It would not be the last. Eventually, Erwin Schrödinger would discover why the electrons were confined to these orbits and not others. He was motivated by a bold suggestion made by the French physicist Louis de Broglie. De Broglie had pointed out that light had both wave and particle-like properties, and perhaps the same was true for matter. When you pluck a guitar string, the string vibrates. But the string can't just have any vibration. The ends of the string are locked in place, and so the waves must also terminate at either end. In other words, the waves on a guitar become quantized. Waves can have a single peak at the middle of the string, or 2 peaks, or 4, but they can never have half a peak, or 2/3 of one. Schrödinger envisioned the matter wave of an electron spreading around its orbit, like wrapping a guitar's neck in a circle. The electron's orbit was quantized and confined to certain distances because its wave had to fit. And this is the picture that was finally revealed in the 2025 experiment, not the electrons themselves, but the waves that describe them. And indeed, this is something key when we explore the atomic and subatomic world. These waves are not real in the same sense as a wave on the ocean or the sound waves that ripple through the air. Schrödinger thought they were physical, that matter smeared itself out across space. But he was wrong. Quantum waves are merely waves of probability. They describe where the particle might be located the next time we go looking for it. Where the waves crest, we have a good chance of finding the associated particle, and where they shrink, the chances are low. And so it is therefore clear that the subatomic world is very different to the macroscopic one. The closer you get to Planck scales, either in terms of size or time or energy, the more the wave nature of reality manifests. And the farther away you are, like in the large-scale world, the more the waves are suppressed. Although the more we explore, the more we are finding the line is drawn much larger than we thought. Indeed, the largest object that has been shown to demonstrate a measurable wave nature is a molecule containing around 2,000 atoms. While the world of quantum mechanics would eventually move on from Bohr's initial crude model of the atom, he was right about one important thing. They exist and have the properties they do because of the intersection of different fundamental forces. If we were to imagine flying a tiny spaceship around inside an atom, we wouldn't see much. The vast majority of it would be completely empty space, filled with nothing but vibrating quantum fields. The nucleus would be a tiny point, a dense ball of positive charge sitting far away at the center. The electrons wouldn't be electrons. They would be invisible quantum waves that, should we decide to observe an electron, would snap out of existence and give us a measurement of its location. And so it is the electromagnetic force competing with quantum mechanics that gives rise to the Bohr radius and the orbits of the electron. And yet deep inside the core of the atom, another series of forces compete with each other to create the nucleus. Atoms are not as simple as their diagrams may suggest. Their nuclei are bundles of even smaller particles, bags of protons and neutrons. Neutrons, as their name might suggest, are electrically neutral. Protons are positively charged, and the two are exceptionally close together, less than a few femtometers apart. At that distance, the electrostatic repulsion is roughly 50 newtons, barely the amount of force needed to lift a watermelon, but that amount of force applied to something as tiny as a proton. Clearly, the atomic nucleus should simply blow itself apart. And yet, it doesn't. Why? The year is 1934 in Osaka Imperial University, Japan. 26-year-old Hideki Yukawa has been up late, fixated on the mystery of why the atom does not simply explode, just as he has been most nights of the past few years. He has tried dozens of attempts to resolve the problem, but nothing seems to work. Unfortunately, he couldn't turn to experiments for guidance. Like Bohr, he wasn't much of an experimentalist. But one late night, long after everyone else has gone to bed, he is struck with a moment of clarity. "The thought suddenly flashed into my mind," he said afterwards, "unbidden, like daylight clearing out the morning fog. A new force of nature could be carried by a massive particle, which resisted the electric repulsion and kept the atomic nucleus stable." What Yukawa started that night would change our entire understanding of atoms, but the significance of the moment didn't strike him. Once I'd published my paper, he later said, I felt like a traveller who rests himself at a small tea shop at the top of a mountain slope. At that time, I was not thinking about whether there were any more mountains ahead. We now call this new force of nature Yukawa proposed the strong nuclear force. To pull a proton or neutron out of a nucleus requires working against this force, like resisting gravity to pull an object from the surface of the Earth. And this means that there is an energy associated with each atomic nucleus. All of nuclear power, from the atomic bombs that can level cities to the reactors that light your homes, is based on extracting this energy. Indeed, if we could harness the nuclear binding energy of all the atoms in a sandwich, it would create an explosion comparable to several megatons of TNT, or a powerful nuclear warhead. And yet, in the full modern picture, the binding of the atomic nucleus isn't fundamental. It is an accident. And that's because the protons and neutrons aren't fundamental either. They themselves are small bags of even smaller particles called quarks. And to understand these, it is time for us to enter a place of worship. The central twin spires rise up gracefully, as if it were a modern-day Tower of Babel. It is a spectacular edifice designed to emulate a French Gothic cathedral. Surrounding the main structure are sculptures, a 21-ton arch depicting broken symmetry, a Mobius strip, a hyperbolic obelisk. This is Fermilab, a particle accelerator outside of Chicago, and in 1995 it was here where the last building block of the subatomic universe finally clicked into place. Two teams working with the Tevatron, which at the time was the world's most powerful particle collider, finally found what they had been looking for after 2 decades of effort: the top quark. The top quark had eluded detection for so long because of its gargantuan mass. Indeed, it weighs over 170 million electron volts. That's 180 times more massive even than a proton. This huge mass means that it takes a lot of energy to create it in the first place, and means that it is incredibly unstable, blinking out of existence almost as soon as it's formed. This particle is the king of the quarks, dwarfing the other 5: the bottom quark, the strange and charm quarks, and the up and down quarks. Quarks are ruled primarily by the strong force, which binds them together through the exchange of gluons. In fact, the strong force is so strong that quarks can never be seen individually. If you take 2 quarks and try to separate them, you have to pour so much energy into the effort that new particles pop into existence between them, including other quarks, that immediately bind to the ones you're trying to pull apart. And so the discovery of the top quark locked in place our understanding of the hierarchy of the atom, and why it has the properties that it does. Imagine an apple the size of an atom. Why does its core shrink to a femtometer, and why does the nearest electron sit a nanometer away? Nature likes to build things out of stable foundations, out of entities that can persist for long periods of time. And so atoms exist at the confluence of the strong and electromagnetic forces and the ironclad rules of the quantum realm, where the balance point is reached between all 3. To begin with, there are 6 quarks to choose from, but the most massive ones destroy themselves long before they have the chance to build anything larger. That leaves the lightest ones with the job to create matter, the up and down quarks, which bind together with the strong nuclear force to make the protons and neutrons. The gluons that carry the strong force have mass, giving them a limited range, a little less than a femtometer. But some of the strong force leaks out of the protons and neutrons. This residual strong force easily overwhelms the electrostatic repulsion between protons, but only for a while, up to a few femtometers, before the gluons give out and the electric force takes over. And it is this that determines the size and shape of the nucleus. the crossover point between these two forces. Indeed, the largest and heaviest element, oganesson, contains a whopping 118 protons stretching across over 1,000 femtometers. It sits right at the limit of how big a nucleus can be before electrostatic repulsion drives protons away. Of course, like the up and down quarks, there are many cousins to the electrons, but they are all heavy and unstable. Again, only the lightest ones survive long enough to participate in something bigger than themselves, and so the electron feels the attraction of the nucleus, but is prevented from reaching it because it can only squeeze its wave function down to a certain limit. And that is how an atom is formed. Out of the quantum chaos of the Planck scales comes the zoo of particles and forces. Certain particles have certain properties that allow them to build things much larger than a Planck length, and in this way, an atom is built, like a bustling city of quantum activity. But of course, the question still remains: why do the subatomic particles, the quarks and electrons, have these specific masses and sizes? This, we truly do not know. It is one of the great mysteries of modern physics. Like explorers in an unknown jungle, sometimes physicists are here just to observe and record, and save true understanding for future generations. But of course, that is not the end of the story, and far from the end of the structures that come together at larger scales. There are more forces of nature and more places of convergence that make much, much bigger objects possible. Out of the cradle, onto dry land, here it is standing. Atoms with consciousness, matter with curiosity. Stands at the sea, wondering, I, a universe of atoms, an atom in the universe. The Chubut River flows through a desert, cutting a green swath set against the flat-top mesas that make up northern Patagonia. And in 2010, a ranch hand, Aurelio Hernandez, was out for a walk when he stumbled across a strange-looking outcropping. Thinking it was a rock, he brushed away the soil to try to clear it, and kept brushing. Eventually, he unearthed a fossilized bone, almost 8 feet long. Over the next few years, paleontologists uncovered more than 200 fossils at the site, and one of the largest creatures to ever have lived. They are called titanosaurs, and you can see one for yourself at the Field Museum in Chicago. Its name is Maximo, and it stretches 122 feet long from tip to tail and stands 28 feet tall at the head. It lived over 100 million years ago, and when it walked the earth, the ground quaked under its 70 tons of weight. Maximo is one of the largest creatures there has ever been, but it doesn't even come close to claiming the crown. The largest living fungus is found in Malheur National Forest in the Blue Mountains of eastern Oregon. There, a single fungal colony spans 3.4 square miles in area and is over 2,000 years old. In its time here on the Earth, it has amassed an estimated weight of over 35,000 tons. That is the biggest. But what about the smallest? While biologists debate if viruses count as living creatures, there is no such question surrounding bacteria. The smallest known free-living bacteria is Pelagibacter ubique, translated as ubiquitous oceanic bacteria, with a length of only a few hundred nanometers. But despite its minuscule size, the species is so numerous that the total mass of all these bacteria outweighs all the fish in the world's oceans combined. And so life stretches across quite a large size range. Indeed, the leap in size between a bacterium and the Malheur National Forest fungal colony is much greater than that of an atom to a bacterium. And yet, when we arrive at this scale, the scale of life, some truly bizarre physics starts to occur. We know that at the smallest scales, between the Planck scale and the simplest living creatures, The universe obeys relatively simple and straightforward physical laws. Forces of nature do their work over certain distances, and particles respond in turn. But there is no equation in physics that can predict how a bacterium might consume food, or how a blue whale might sing its song. Standing between the laws of nature and biological systems aren't just many orders of magnitude. There is also an unimaginable jump in complexity. And this is the concept of emergence, how simple rules can lead to surprisingly complex behaviors. And the best way to illustrate this is through a game. To begin with, imagine a series of cells forming a grid. Choose whichever cells you want to be alive. They are activated. Then proceed as follows. Any live cell with fewer than 2 live neighbors dies, as if by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. But any live cell with more than 3 live neighbors also dies, as if by overpopulation. And finally, any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. This is the game of life, created by mathematician John Conway. First appearing in an issue of Scientific American in 1970, it shows how complexity can arise from a set of simple rules. Indeed, 2 games of life with only slightly differing starting arrangements can lead to wildly different outcomes, with different patterns, arrangements and structures appearing and disappearing, and sometimes even coming back unexpectedly, dozens of iterations later. Conway's game of life is so complex that it's what's called Turing complete, meaning that it can, with sufficient preparation, act as a fully programmable, general-purpose computer. This means that anything you do with the chips and software in your smartphone can be done with a suitably large game of life. And emergence is a property not just of computer games. It is found everywhere in the real world. Just because the world is governed by fundamental laws and rules doesn't mean that we can use those laws and rules to describe everything about the world. For example, each individual bird in a flock only follows a simple set of rules, but the entire flock moves in unpredictable ways. No single ant knows how to build a colony, and yet a colony emerges when enough ants get together. And it's not just living creatures. Individual molecules of hydrogen and oxygen are not wet. Wetness emerges from countless interactions among trillions of molecules. And of course, scientists believe that our conscious experience of the world is rooted in the fundamental forces of nature, and yet we have no way of explaining our consciousness. And so at some point, billions of years in the Earth's past, molecules made the leap from inorganic to organic, an emergent leap that still today defies easy explanation. A single living organism, even a single bacterium, is perhaps the most complex structure to be found in the entire universe, with information, energy, and interactions zipping up and down 10 orders of magnitude in scale. And of course, this is the scale of us, of humanity, an interplay of interactions largely dominated by the electromagnetic force. Electromagnetic repulsion and attraction, the sharing of electrons as wave functions overlap, and so on. This force binds electrons to nuclei and atoms to each other. It pushes, pulls, repels, draws, and mixes. Atoms become molecules, molecules become compounds, compounds become living tissue. A sodium ion penetrates a membrane in a neuron, electromagnetism. Your heart beats a little faster, electromagnetism. The touch of a lover's skin against yours, electromagnetism. And it is electromagnetism that places limits both on how small and how large a living creature can be. The smallest organisms need to be complex enough to carry out the basic functions of life, reproduction, gathering of nutrients, and so on. So there must be a minimal number of atoms and molecules present. And as for the largest creatures, electrical and chemical nerve signals can only transmit information and instructions so quickly. Indeed, that's why the great sequoias and fungal colonies can be so much bigger than Maximo the dinosaur or the largest blue whales. They don't have to move or react in real time. But even amongst these more sedate greats, electromagnetism sets a limit, and that is through heat. Each cell within any living creature captures, stores, and releases energy. Like tiny little motors, each of these processes releases a small amount of heat, and repeated again and again. There are 30 to 40 trillion cells in the human body alone. Every creature ends up having to solve the problem of heat. This is why large animals, like the elephant, have huge ears and no hair to radiate heat. The largest land animal possible is estimated to be around 120 tons, just a little bit bigger than Maximo, for exactly this reason. And finally, all of life, mediated by the electromagnetic force, operates at a scale so important that we defined it as the common measure of all things. Only a few hundred years ago, systems of measurements were based on everyday experience. A foot is roughly the length of, well, a foot. It is divided into 12 inches because it makes it easy to create a variety of fractions. An acre was the amount of land a farmer and a team of oxen could plough in a single day. But the French Revolution wanted a better system. This was to be a new country based on reason, logic, and science. And so the French Academy of Sciences devised a new standard of length. The meter, equal exactly to 1/10,000,000th of the distance from the North Pole to the equator on a line passing through, of course, the Paris Observatory. And in 1983, this definition was revised. The meter was now the length of the path travelled by light in a vacuum in 1/299,792,458th of a second. The meter was now defined using a fundamental constant, the speed of light, rather than measured independently. And with this definition in hand, we have taken the measure of the cosmos, all the way down to the Planck scale. A single Planck length has to be multiplied almost a billion times to reach a meter, the standard of the macroscopic world. All of life happens in and around a meter, from the nanometer to the tens of meters. And when we peer into the apple, we see just how dazzlingly complex the machinations of life are, all contained within those scales. Within each cell is a bustling city, a veritable biochemical metropolis. For defensive walls, they have a cuticle made of fatty acids. Instead of government offices, they have a nucleus, home to the DNA. Instead of police officers and firefighters and engineers, they have proteins and enzymes that go around fixing, repairing, breaking down, rebuilding, and warding off invaders. And instead of power plants, they have mitochondria, which converts sugar into usable energy, or the chloroplasts, which turns sunlight into sugars. And so everything within the apple's cell is governed by the force of electromagnetism and, at the smallest scales, the strong and weak nuclear forces. But of course, that's only 3 of the 4. There is still one force left to go. For at far larger scales, scales bigger than even the greatest living creatures, gravity comes into its own. Thus, we come to see that if our bodies are made of star stuff, and there is nothing else, says the spectroscope, to make them of, we are made of universal and divine ingredients, and the study of the stars will not let us escape a wholesome and final knowledge of the fact. It is time for a road trip across the surface of the sun. Our craft leaves the northern polar regions going south at a leisurely pace of 70 miles an hour, your average morning commute. The poles themselves are regions of intense activity, as magnetic fields twist and wind and plunge their way down into the surface. And alongside this magnetic activity come convulsions of plasma, as huge mountains of it, half the size of a planet, rise up and collapse in a matter of hours. Before long on our journey southwards, we encounter our first granule, one such chunk of erupting sun stuff. There's bound to be some turbulence in this region, which spans some 1,500 kilometers. It will take most of a day to make the crossing. After a few days, we reach our first sunspot, a massive cavity opened up in the sun as immense magnetic fields punch down through the plasma, a yawning chasm 1,000 kilometers deep. This one, however, is roughly medium-sized, just over the width of the Earth. At our sensible speed, we will reach the other side in a few days if we don't stop for toilet breaks or sleep. As we crawl onwards, we are met with prominences and flares, great arching structures as magnetic fields funnel stellar material out into space. These eruptions are unpredictable, and at their peak, they can stretch for 1 million kilometers or more into the darkness before plunging back down, taking up so much volume that they could cradle all the planets of the solar system in their embrace. And yet, we've barely gotten started. At the present pace, our craft will reach the equator of the Sun, completing a voyage of 1/4 of its entire circumference in a little over a year. Best to bring a snack. Ancient people believed that the Sun and the Moon were the same size, and in a sense, they are. By sheer cosmic coincidence, the Sun is roughly 400 times wider than the Moon, while sitting roughly 400 times further away. And it is because of this coincidence that Earth is the only planet that gets to enjoy perfect total solar eclipses. And yet even at the great distance of 150 million kilometers away, the Sun is still powerful enough to melt the ice in your drink on a warm summer afternoon. Indeed, it's for the best that the millions of kilometers between us are nothing but vacuum. If the sound produced by the Sun could reach the Earth, it would be louder than standing next to a jet engine during takeoff. Every single second of every single day. This is because the Sun is by far the largest object in the solar system. In fact, from a certain perspective, the Sun is the solar system, with all the planets, including Jupiter, nothing more than rounding errors and extra decimals added onto the mass and radius of our parent star. The Sun alone contains 99% of all the material in the system, 1 million of our Earths could fit within its volume, and even mighty Jupiter can do nothing more than barely nudge and tweak the position of the Sun as it orbits around it. Indeed, the Sun is roughly 10 to the power of 44 Planck lengths across, the Earth roughly 10 to the power of 42. But why is the Sun so much bigger than the Earth? Well, as with all the layers that came before, the answer lies at the intersection between two competing forces. In Sudbury, Ontario, in Canada, over 2,000 meters beneath the Earth's surface, sits an unused mine shaft. No sunlight pierces these depths, just the warmth of the surrounding miles of rock, bringing the temperature of the mine shaft to a sweltering 50 degrees Celsius. And at the center of an otherwise empty chamber is a strange piece of technology. It looks like a sort of cosmic egg left long dormant. But this was not the work of aliens. It was built by astronomers. And yet the instrument had no mirrors, no lenses, no refractors. Indeed, it couldn't even see the sky. But it could peer right into the heart of the Sun. And in May 1999, a team of astronomers activated it. The observatory consisted of a geodesic sphere containing 1,000 tons of heavy water, donated to the experiment by Atomic Energy Limited of Canada at no cost, and a market value at the time of over $330 million. Mounted across the surface of the sphere were 9,600 photomultiplier tubes, each one designed to amplify any feeble flickers of light within the water. This was the Sudbury Neutrino Observatory, which for 7 years watched as tiny, ghostly particles streamed through it. The observatory had been designed to solve a decades-old mystery about the Sun. At the opening of the nuclear age, physicists had realized that fusion powered the core of our star. Every fusion reaction produces a neutrino, the tiniest of the fundamental particles. Indeed, every single second, hundreds of trillions of solar neutrinos pass through your body. But previous experiments could only detect roughly 1/3 of the expected amount. Did this mean that the Sun was actually 2/3 smaller than it seemed? No, of course not. The answer lay within the neutrinos. Neutrinos come in 3 types, known as flavors. And unlike previous experiments, the Sudbury Neutrino Observatory could measure neutrinos in two ways. It could detect just one flavor, but it could also simultaneously measure the total number of neutrinos passing through. And after years of analysis, the Sudbury Neutrino Observatory demonstrated that neutrinos could change flavor as they travel. This experiment rocked the physics world and created a mystery known as neutrino oscillation that persists to the present day. But it also confirmed that fusion, and fusion alone, makes the sun shine. Every single minute, the sun consumes roughly an Earth's worth of hydrogen, fusing it into helium in the core at a temperature of roughly 10 million Kelvin. Each conversion leaves behind a little bit of mass, which translates to a little bit of energy. Multiplied again and again, the sun produces more energy in a single second than the entirety of humanity uses in 100,000 years. And so as the massive weight of the sun, the force of gravity, pulls inwards, resisting that is the energy released from fusion, which pushes outwards as the flood of radiation tries to escape the core. Ever in balance, the two forces maintain equilibrium, with one never quite winning the battle against the other. This balance, however, does mean that stars can only exist in a certain range of sizes. At the small end are the red dwarfs, stars so small and dim that their feeble light is mostly in the infrared region of the electromagnetic spectrum. The smallest known star is EBLM J0555-57AB. Sitting about 600 light-years away, the star is only about 88 times the mass of Jupiter. It's right at the limit. Any smaller and its own gravitational pull would be too weak to ignite fusion in its core. It's less than a tenth of the mass of the Sun, and it's so small that it only has a radius roughly the same as the planet Saturn. Smaller than this are the brown dwarfs, strange hybrid objects that straddle the ambiguous boundaries between planets and stars. Shortly after formation, they briefly fused deuterium in their cores, but then they sputter out, spending the rest of their lives merely cooling off. Red dwarfs are by far the most common kind of star. Roughly 2/3 of all the stars in the Milky Way are red dwarfs, and even the nearest star to the Sun, Proxima Centauri, is a red dwarf, but it's so dim that it's invisible to the naked eye. And at the other end of the spectrum are the true giants of the galaxy, the largest stars. The biggest stars are so big that it's difficult to ascertain their true extent. Their surfaces are bloated and extended, constantly in flux as they swell and contract in violent spasms that reveal their inner nuclear turmoil. Along with that, their brightness changes over the course of days, making it extremely difficult to measure for sure. And when it comes to the most massive, most luminous, hottest star known, analogy fails. Sitting 136,000 light-years away, R136A1 lives in a satellite of the Milky Way, the Large Magellanic Cloud. It weighs nearly 300 times the mass of the Sun and emits so much light that it outshines 1,000,000 suns. But it's so hot that most of its output is in the form of ultraviolet radiation. Indeed, to the naked eye, R136A1 is only 164,000 times brighter than the Sun. At the distance of Proxima Centauri, just under 4 light-years away, it would outshine the full moon. R136A1 exists right at the limit of the most massive star possible. This is because heavier stars have more gravitational pressure in their cores. More gravitational pressure means a higher rate of nuclear fusion. More nuclear fusion means more radiation, and more radiation means more energy poured into the body of the star. At a mass higher than 300 solar masses, the core of any star would produce so much radiation that it would blow itself apart in a furious burst of energies, something akin to a supernova explosion at the moment of its birth. However, that's just the limit today. Modern-day stars contain traces of elements heavier than hydrogen and helium. These elements absorb light, affecting the delicate balance between gravity and radiation and governing stellar sizes. But in the early universe, the first stars had no such limits, and astronomers believe they may have swelled to sizes 10,000 times the mass of our Sun or more. There are only two kinds of objects larger than stars in any galaxy, and they represent the start and end stages of the dance between radiation and gravity that makes them possible. Stars emerge from giant molecular clouds, vast complexes of gas and dust that drift loosely through the galaxy, barely held together by their own gravity. When perturbed, a gas cloud contracts under its own weight, producing dense pockets that eventually reach the critical densities needed to ignite nuclear fusion. Indeed, a single cloud has enough material to produce hundreds and even thousands of stars. The largest known cloud is called Sagittarius B2, which stretches 150 light-years across, or roughly 10 to the power of 18 meters, and weighs 3 million solar masses. Located near the center of the Milky Way, Sagittarius B2 is also home to the other largest object in the galaxy, Sagittarius A star. This is a supermassive black hole, the ultimate end result of a star's life when its nuclear fuel is extinguished and gravity finally wins. Sagittarius A star is the largest of the black holes in the Milky Way, weighing a tremendous 4.5 million times the mass of the Sun. And so, an apple the size of a star, roughly 1 billion meters across, would not last very long as an apple. Almost immediately, the force of gravity would take over, compressing the core of the apple to nuclear densities. Once fusion ignites, the temperatures of the rest of the apple would climb to thousands of degrees, turning it into a plasma. For millions of years, the competition between radiation and gravity would keep the apple at a stable size until the light would give out and gravity would finally win. And indeed, when it comes to even larger scales, gravity almost always conquers all. Almost always. I have looked farther into space than ever a human being did before me. William Herschel was born in 1738 to Isaac and Anna. His father was an oboist, his brother was an oboist, William was an oboist. Although to be fair to William, he was more than an oboist. He also played the violin, harpsichord and organ. He composed 24 symphonies as well as concertos and church music. But he was also ambitious, always scheming and plotting to advance up the social ladder. And so, in addition to his musical pursuits, he also decided to engage in the most gentlemanly of trendy pastimes: astronomy. He built his own telescopes, ground his own mirrors, and proceeded to make his mark on the stars. Quickly, he racked up achievement after achievement, including discovering Uranus, spotting new moons of Saturn, and recording the seasonal changes in the Martian polar ice caps. But this was still not enough. And as a final crescendo to his astronomical career, he attempted to create a map of the entire universe. To make this map, Herschel assumed that the stars were all the same brightness, and by looking in particular directions, he would measure the total brightness, giving him an estimate of the distance to that location in the universe. For the time, his map was astonishing, revealing a picture of a flattened, elongated universe, the precursor of our present understanding of the disk of the Milky Way galaxy. If only that oboist could see the maps we make now. And in 2022, after several years of operation, the European Space Agency's Gaia satellite released the largest catalogue of stars ever produced, standing at nearly 2 billion. It was an incredible number, and yet less than 1% of all the stars in the Milky Way. Spanning over 100,000 light-years, containing over 1.5 trillion solar masses of stars, gas and dark matter, and roughly 10 to the power of 56 times bigger than the Planck length, the Milky Way is, as galaxies go, rather average. Indeed, it is dwarfed by our nearest neighbour, the Andromeda Galaxy, which hosts an estimated 1 trillion individual stars, more than double the Milky Way. 220,000 light-years across. If you travelled at the same speed that took our car many months to make progress across the face of the Sun, you would have to drive for well over 1 trillion years to make it from one end of Andromeda to the other. And indeed, the largest galaxies make even these giants seem tiny. At the centres of galaxy clusters sit their most massive concentrations of matter, the brightest central galaxies. These are the downtown cores of the cities, filled with stellar high-rises and super-tall skyscrapers. The largest of these galaxies is known as ESO 38376, a galaxy so enormous that it defies description except by bare numbers. It spans 1.8 million light-years in diameter and weighs up to 10 times as much as Andromeda. A crossing here would take 20 trillion years, more than 1,000 times the current age of the universe. Galaxies are what happens when gravity, by far the weakest of the forces, has time enough to play. In a way, at large enough scales, no other fundamental force matters. The universe is on balance electrically neutral, and so the electromagnetic force holds no influence. And the strong and weak nuclear forces are limited to subatomic scales. They can't influence anything beyond their minuscule borders. And so in terms of fundamental forces, gravity, and only gravity, shapes the grandest structures in the cosmos. All it takes is time. For gravity may be weak, but it is persistent. All it takes is the tiniest seed, a small difference in density. That small seed will attract its surroundings, helping it grow. With even more mass, the pull becomes stronger. More and more, the rich growing richer. Over millions and billions of years, the universe assembled the galaxies out of the thin, uniform fog of the primordial cosmos. And gravity is not yet done. For beyond the bounds of the Milky Way galaxy sit structures that seem to embrace the heavens themselves, grand walls and glittered canopies spanning tens of millions of light-years on a side, the culmination of billions of years of gravitational effort. Surrounding the Milky Way is a ring of 12 galaxies, each sitting roughly 12 million light-years away. These galaxies are the nearest portion of the local sheet, the Great Wall in which our galaxy is embedded. Indeed, they are simply the nearest edge of that sheet, but their circular arrangement around the Milky Way has inspired astronomers to give them a name of their own: the Council of Giants. And in July 2020, an international team of astronomers discovered something even larger. Using archival data from the Spitzer Space Telescope, the team managed to pick out dim galaxies peeking through the so-called zone of avoidance, the region of the wider universe that sits beyond the dense veil of nebulous gas in the core of the Milky Way. Through there, they identified a structure almost beyond description. Called the South Pole Wall, it is a filament of hundreds of thousands of galaxies extending for over 1.3 billion light-years from end to end. To get a sense of its extent, its ends are anchored behind constellations in two different hemispheres, Perseus in the north and Telescopium in the south, which are a full 145 degrees apart, nearly on opposite sides of the sky. If we were to drive the full length of the South Pole Wall, it would take 1,000,000 trillion years. And it might be bigger. The astronomers involved in its discovery admit that they don't know if they've completed their survey. "We are early explorers of the cosmos," said lead astronomer Brent Tully of the University of Hawaii, extending our maps into unknown territory. And so, just how big is the entire universe? So far, with our most powerful galaxy surveys, we've mapped out some 10 million galaxies of the suspected 2 trillion that inhabit the observable universe. We know that these galaxies twist and lace their way through filaments, intersecting at clusters and tracing a pattern that resembles a gigantic spider's web. This cosmic web is the largest pattern found in nature, filling up the observable universe from end to end, with massive voids left between the glittering braids. And pocking the cosmic web at these vast distances are subtle imprints. They are invisible to the eye and only reveal themselves as shells of slightly higher galactic density. These are the leftover echoes from when massive sound waves crashed around the very early universe. They are called baryonic acoustic oscillations, or BAO. A single BAO shell can be up to 1 billion light-years across. Just like the galaxies and the cosmic web, the size of the universe is determined by gravity. Indeed, the contents of the universe set the expansion rate and the time since the Big Bang. The rest is history. But the true extent of the universe is unknown. Indeed, for centuries, astronomers had believed the universe to be infinite. But of course, in an infinite universe that is also infinitely old, no matter where we look, we should see a star. Even accounting for the relative slowness of the speed of light at cosmic scales, with enough time, the sky should be ablaze everywhere with infinite light, even in the depths of night. And with the revelations of the Big Bang Theory, we discovered that the universe we can interact with is not infinite. It has an age, and because of that age, it has a limit. The universe is only so old, the speed of light only so swift. The sky is not illuminated with the light of infinite suns, because the universe is not infinitely old. In fact, the expansion of the cosmos carries galaxies away from view, permanently. At great distances, the recession of distant galaxies can exceed the speed of light. We can still see other galaxies, for now, but that's because their light left long ago. By the time their light reaches the Earth, billions of years later, the galaxy is long gone from view, carried away by the inexorable cosmic expansion. And so, the entire universe could be infinite. Perhaps we will never know. Like a lantern lit in a dark forest, our entire existence is defined by this sphere of feeble and flickering illumination. That sphere is 93 billion light-years, or roughly 10 to the power of 62 Planck lengths, in diameter. That is the distance to the edge of the cosmological horizon, the largest possible scale that we could ever measure in the universe. And all that exists on these largest scales, from the galaxies and the cosmic web to the ultimate horizon of the universe itself, was dictated long ago. For gravity may control the fate of the universe and be the invisible hand that sculpts the great creation, but it was not the instigator. It was not what set it all in motion. And this is linked to the biggest mystery in the universe. For at roughly 100 megaparsecs or so, the universe evens out. With no larger structures or differences from place to place within the cosmic web, this is called the scale of homogeneity, or, somewhat more dramatically, the end of greatness. This is the mirror image of the Planck scale, roughly 10 to the power of 59 times larger than its twin, the other end of the universe. At the Planck scale, reality is nothing but chaos. At the homogeneity scale, everything is the same. Why? At the very earliest epochs in the universe, when the entire observable universe was compressed to scales even smaller than the Planck length, unknown forces were in action. They set the universe in motion, and through quantum creativity wrote a story that would be told over the coming ages. And we call this event inflation. This is a hypothetical period that occurred when the universe was less than 10 to the power of minus 35 seconds old, and it was over and done with by the time the universe turned 10 to the power of minus 34 seconds old. In that briefest flicker of time, the cosmos became much, much larger, growing in size by at least 10 to the power of 50 orders of magnitude, reaching the comparatively dizzying proportions of an entire atomic nucleus. And so inflation made everything bigger, even the quantum fluctuations that only exist at the Planck scale. Now made microscopic, those fluctuations imprinted themselves on the fabric of space-time, leading to pockets of slightly higher density scattered across the vast expanses of the universe. And these were the seeds that started it all. What would follow would be the weaving of the cosmic web itself, the smallest possible fluctuations in the universe intimately connected through strands of gravity to the largest pattern in nature. And this is the homogeneity scale. These quantum fluctuations blown up to countless trillions their original size and averaged out across the cosmos. And so now, for the final time, we can return to the apple. An apple at this scale would completely change the course of cosmic evolution. It would take eons to play out, as sections of the apple splintered off and collapsed in on themselves, slowly imploding under their own weight to become galaxies in their own right. But at cosmic scales, a balance would shift. The present-day universe is ruled by dark energy, a mysterious force that is accelerating cosmic expansion. But even if we were to eliminate dark energy, or if it were to fizzle out and disappear, the expansion would not stop. There's simply not enough matter with enough mutual gravity to halt expansion. Indeed, the universe is achingly thin, with an average density of just 1 hydrogen atom per cubic meter. An apple, however, is far, far denser than that. An apple tens of gigaparsecs across would be more than enough to slow cosmic expansion, to halt it, and even reverse it. The future universe would then be smaller than the past, the Big Bang turning into a big crunch, with the endpoint a singularity of infinite density, the same mysterious state that gave birth to the cosmos 13.8 billion years ago. We do not know why the universe is the way it is, why it's filled with so much matter and so much dark energy. The present-day universe could have been much smaller or much larger had anything been different in those early quantum forges. There are only 4 known forces in the universe, and 3 generations of each of the particles. Together they dance and weave and intersect, sometimes colliding, sometimes colluding. At the smallest of scales, all the forces meld together into an incoherent mess, and at the largest, only gravity remains. In between is everything else. The atoms, life, the stars, the galaxies, each one bound by a set of rules that governs their respective domains. And so perhaps that is the secret as to why the apple, and us, is at the center of the 62 orders of magnitude that span reality. We sit at the confluence of all the forces of nature, each one working in its own way to influence what happens here on the surface of the Earth. At the smallest quantum scales, gravity holds no sway. At the largest, the other 3 fall silent. But here, on the Earth, at scales of roughly a meter, everything comes together. The strong nuclear force binds together the atoms. The weak nuclear force transforms them and creates the table of elements. Electromagnetism holds electrons in their shells and glues the atoms together to make molecules and the dance of life. And finally, holding everything together is gravity, giving us a solid foundation under our feet and an anchor for our oceans and air. All the forces of nature, across all 62 orders of magnitude that measure existence, work together right here at the apple, the center of the universe. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.